Okay, thank you very much for the kind introduction, and let me thank the program committee for giving me the opportunity to talk about our work, and the organizing committee for making this event such a wonderful conference. Now, you've heard this already in some of the previous talk during the conference. There's a number of grand challenges in physics still. We don't know how to unite all four fundamental forces. We don't know what most of the universe is actually composed of because we don't know what dark energy and dark matter are. And we don't even know why we exist because we cannot explain the apparent antimatter-matter asymmetry. And none of these effects is actually part of the standard model of particle physics, our current best description of nature. Now, if you look at these questions, you might be tempted to think that you should go into cosmology to search for answers resolving those questions, or maybe go to high energy physics, large accelerators, where you can look for new particles at very high energies that are not part of the standard model yet. But I would like to tell you that quantum optics and metrology in the low energy but extremely high resolution limit can provide answers to these grand challenges as well. And we've seen in John Doyle's talk, for example, a few days ago already that these low energy, high resolution experiments start to outperform results obtained, for example, at large accelerator facilities. Now, in terms of precision spectroscopy, there's a number of experiments that you can do to try to tackle these questions. Essentially, what we do is we try to find additional holes in the standard model that cannot be explained and hope that this will provide us a glimpse in which direction to actually search for a new, more refined model. Now, one of these things that you can look for that's also forbidden by the standard model is a possible variation of fundamental constants, such as the electron-to-proton mass ratio. And you do that by comparing, so if mu would change this ratio, then your favorite level system would change, and you compare it to another system that does not change or changes in a different way. And you can do that with molecules, in particular in a model-free environment. Now, we can also do tests of the standard model, for example, by probing for fifth forces or probing for QED using molecular ions, for example, Hd plus H2 plus, and we've heard in Tanya Zelevinsky's talk her work on strontium-2. Parity violation, we've also, you can perform spectroscopy on molecular ions, or you can look at energy splitting in chiral molecules, because if parity is broken, then molecules of different chirality will have slightly different energy, ground state energies. And we've heard, for example, in Ed Heinz's and John Doyle's talk, you can search for an electric dipole moment of the electron by performing molecular spectroscopy of selected molecular ion species, because they provide the very strong internal electric field that you need to become sensitive to such a dipole moment. Now, if you look at the species, in particular for the ion species that I've listed here, then you will see that these are not probably your favorite molecules. You cannot control them in the way that we can currently control atoms, and therefore we need new techniques, and I would like to advertise that I think that quantum logic spectroscopy is such a technique to unleash the potential of molecular ions. Now, how does quantum logic spectroscopy work? We like to work with single-trapped ions because of accuracy, that we can get the highest accuracy. So you trap your spectroscopy ion that you're actually interested in together with a logic ion, and they're coupled via the very strong Coulomb interaction, and that allows you, through a series of laser pulses, to actually transfer the internal state from the spectroscopy ion onto the logic ion and detect the internal state there. That goes both ways, of course, so you can also use the logic ion to control the internal state of your spectroscopy ion and do state preparation. So in a sense, this compound system combines the advantages of both species that you have, the interesting spectroscopy features of the spectroscopy ion, and the excellent controllability of your logic ion. And that will allow you to investigate new types of species. Now, in my group, everything revolves around this quantum logic spectroscopy, and I will give you a few examples, namely molecular ions and quantum engineering in my talk. That brings me to the outline. I will show you how we can detect the internal quantum state of a molecular ion non-destructively. It's a QND measurement, and we don't destroy the molecule while detecting it. And I will then show you how we can enhance the detection fidelity here by using non-classical states of motion, in our example, Fock states of motion. And then I will provide a very brief glimpse on the new frontier in spectroscopy, which is spectroscopy of highly charged ions. Now, why do we want to work with trapped ions? Trapped ions is an excellent platform for precision spectroscopy because we have large trapping frequencies in linear ion traps, such as this Innsbruck-style blade-type trap. We achieve trapping frequencies on the order of few megahertz that allows us to perform recoil-free spectroscopy. We can have very long storage times, between hours and months of ions in such traps, and that allows us to achieve very long interrogation times. Now we trap the ion in the zero field, which results in very small trap-induced shifts that we can measure very accurately and subtract from our measurement. Now, combined with laser cooling and the fact that the ions are separated by a few microns in the trap, we do not have any interactions except for the Cooler interaction between the ions that does not factor into the spectroscopy signal. And therefore, we can achieve very high accuracy. And I would like to take this opportunity to advertise a poster by David Hume, where he shows that the NIST aluminum clock now has reached, for the first time, a clock has reached a level below 10 to the minus 18 systematic uncertainty. Now, what are the requirements to achieve such mind-bogglingly high systematic uncertainty? You need to first laser cool your system to reduce Doppler shifts. We do that via laser cooling in atoms. You need state preparation, which we usually do via optical pumping. You then need to probe, of course, your clock transition. And you need to detect whether you've made the transition via electron shelving techniques. Now, in molecules, it's much harder. You would like to do the same thing, but most of them actually don't work for all molecules. Yeah? There are some molecules, and we've seen that in Ed Heinz and John Doyle's talk, that you can laser cool with a reasonable amount of repumping lasers, and you can also do optical pumping, but that does not work in general. Yeah? These are very selected species. And the reason is, of course, that there's typically no closed cycling transition available in molecules. Now, how have people performed molecular ion spectroscopy in the past? The cooling that the neutroatom people are very much concerned about is actually not an issue in our case. Because of the strong Cooler interaction, we can provide sympathetic cooling of co-trapped cooling or logic ions. As you can see here in this little movie, the bright dots are magnesium ions, and the voids that you see here are occupied by molecular ions, and the fact that the voids are localized until a collision event occurs tells you that the molecular ion is cold as well. And in fact, when we decided to start working with molecules, the day after we had our first molecule, we had it in the motional ground state. So cooling is really not an issue with molecular ions. And we and others have, in the meantime, not only sympathetically Doppler-cooled molecular ions, but also ground state-cooled them. Now, state preparation is an issue, and there have been a number of techniques developed to prepare the initial state of the molecular ion with collisions using neutral atoms, optical pumping with a number of repump lasers, or state-selective ionization. Common to all of these techniques is that they're fairly slow, and if you work with a single ion, which we want to do to get a low systematic uncertainty, your data rate droops and you cannot get the statistical uncertainty that you need. The same is true for state detection. There have been a number of techniques developed. So, for example, state-dependent chemical reaction or state-dependent dissociation. All of these techniques are destructive, so you lose your molecule after detection. And for this reason, you need to work with clouds of molecules. And again, we don't want to do that, so we need new techniques to achieve all of this. So no fast cycling transition restricts sort of what we can actually do, our quantum control over the molecules. And that is one of the reasons why the systematic uncertainty for optical spectroscopy in molecular ions is currently at 10 to the minus 9 versus a 9 order of magnitude lower systematic uncertainty for trapped atomic ions. And we want to develop a toolbox that brings molecular ion spectroscopy to the level of atomic ions using quantum logic. Now, how does it work? It's the same picture as before. We trap the molecular ion together with our logic ion, in this case magnesium and magnesium hydride. We map the molecule's internal state into a motional state, and that's a joint motion, a coupled motion between two ions, and we read out the change in the motional state on the magnesium ion, on the logic ion. And this way, the atomic ion is a sensor for the molecular ion. We can control its internal state through the atomic ion, and therefore bring molecular spectroscopy to the level of atoms. Now, let me briefly introduce to you our molecular ion, magnesium hydride plus. It has an electronic transition at around 280 nanometers. If you zoom in, you see that the vibrational level structure here, and the vibrational constant is so large that the molecule is dominantly in the vibrational ground state at room temperature. Now, there's also rotation, of course. If you zoom further in here, you see the rotational bands, and the rotation is coupled by black body radiation that leads to a thermal distribution of rotational states. And if you have a single ion and you prepare it in, for example, the rotational ground state, you can see in this quantum Monte Carlo simulation how the rotational state evolves under black body radiation coupling. And what's interesting is that the mean dwell time in the higher levels becomes shorter. And for this and other reasons, we've decided to actually detect the molecule in the J equals 1 state, because the dwell time here is on the order of seconds. Now, how do we do that? We implement a state-dependent dipole force, and the dipole force is actually oscillating. So we have two Raman-type beams counterpropagating that provide an oscillating dipole force and excites a common motion of the two-ion crystal if and only if the molecule is in the J equals 1 state. And how do we do that? So you can view that as an oscillating dipole force or a Raman transition on the motional sideband here that generates a displacement operator effectively. Now, you can pick essentially the rotational state that you're addressing by choosing the detuning of this laser. And here's a portrait chart diagram where you can see all the resonances between the electronic ground and excited state and the rotational bands. And if you zoom in, you can see that the J equals 1 state is fairly isolated. So if we choose our detuning to be around these areas, we exclusively couple to the molecule when it's in the J equals 1 state, and there's no coupling or negligible coupling if it's in any other rotational state. Okay, so we get rotational state selectivity through the laser detuning. Now we have an offset signal from the atomic ion that has also a resonance near the same wavelength. And so we need more advanced control techniques that I unfortunately don't have the time to talk about. We call it a motional qubit that allows us to manipulate the motional state just as a spin 1/2 system. Now, how does the experiment look like? We prepare the motional ground state of this 2-ion crystal in the axial direction. Then we apply the spin motional coupling, the more complicated scheme. We apply the optical dipole force, map it back, and then detect on the magnesium ion. And here you can see the fluorescence signal on the magnesium ion while the molecule is driven via black-body radiation between different rotational states. If it's in the J equals 1, the application of the optical dipole force excites motion. We see that as an increase of the detection signal in our magnesium ion. And so what you've seen here is actually a quantum jump of a single molecular ion being driven by black-body radiation into the J equals 1 rotational state and then leaving that state again. And that's sort of life in the laboratory. Now, of course, signals like this you get all the time in your lab if some laser falls out of lock, so you need to prove that this is actually from the molecule. And we've done that by changing the detuning, and we've mapped out essentially this dispersive resonance or force profile that we can exert on the molecule. Now, of course, this is just a demonstration experiment. This is not a narrow line, but at least it agrees with previous measurements. And in the future, the idea would be to extend techniques similar to this to narrow line spectroscopy. Now, what is the limitation here? I have to admit that the data rate in this experiment was fairly low, and the main limitation is residual off-resonance scattering of the molecule and then losing the molecule to another rotational state. Now, we have typical off-resonance scattering probabilities of 4%, and after 30 cycles of averaging for each of these data points, there's a 70% depumping probability. Now, what can you do about this? You can implement high-fidelity operations to cut down on the quantum projection noise to require fewer averaging cycles. You can, and you need to apply the optical dipole force as short as possible. But if you apply too short, your signal also dies away, and so you cannot really do that. Now, the solution that we have come up with is the use of non-classical states of motion to enhance your force detection sensitivity. And that's the next topic. We've used motional Fock states to achieve this goal. Now, our classical detection scheme works like this in the simple variant. We prepare the motional ground state. We then apply apply displacement force. That's the optical dipole force that displaces in this phase-based representation here the motional ground state. And then we measure the overlap with the original vacuum state. And that gives us our signal. You can see that very nicely in this Wigner phase-based presentation. You can see the original and the displaced Wigner function down here, and up here you see the product, and we measure essentially the integral over this product. Now, as the displacement continues, you see that the overlap approaches 0 exponentially. And the slope here gives you the sensitivity to actually detect displacements. Now, looking at this, an idea that might occur to you is you can use squeeze states, for example, to enhance your displacement detection efficiency. And that has been done by many groups like Wineland, Home, and others. Or you can use Schrödinger cat states that has been beautifully demonstrated by the blood group to detect scattering of single photons, where you generate a cat state, then you displace the cat state and you recombine, and your signal is essentially the phase accumulated during the scattering of the photon here. Now, these two techniques are require both phase control, so you need to know in which direction you actually want to apply your displacement such that the displacement and your squeezing or your Schrödinger cat state are aligned for maximum sensitivity. And we didn't have that feature. We did not have phase control in our experiment. So we came up with the Fock state spectroscopy, because Fock states are symmetric but still can give you quantum gain. Now the sequence looks like this. We prepare again the motional ground state. We then apply what we call a blue sideband that excites one quantum of motion into the system. We then apply the displacement and end up with a displaced Fock state. And then we measure the overlap with the initial Fock state that we've created. Now, if you do that again, you can visualize this in this Wigner phase space representation. And you see here the original Fock state and the product of the two Fock states. And as the displacement commences, you can see that we get interference here from the negativity of the Wigner function. That leads to a steeper slope here and some oscillations here. And we take advantage of the initial steeper slope for our measurements. Now, how does it work in the experiment? We do experiments for demonstration purposes just with a single magnesium ion. We apply an electric field tickle to excite the motion of the ion at the trap frequency. If we do that displacement operation with the vacuum state, we expect theoretically the dash curve and see experimentally the solid line as a fit to the data. If you do that with a Fock state, you can see that the contrast is somewhat reduced here, but the slope is much larger. And we can even do that with the Fock state n equals 2. And again, the slope is enhanced here. Now, to really be able to tell whether we get any metrological gain from doing that, we use a toolbox of quantum Fisher information that tells you the maximum achievable sensitivity that's given by the Crayer-Ramo bound. And the Fisher information is here. And the larger the Fisher information, the smaller your statistical uncertainty of the measurement. Now, the classical limit for the Fisher information is 4, which is this red line here. And you can see for the vacuum state, you would expect theoretically a sensitivity or a Fisher information as the dashed curve, and experimentally we observe this curve here. Excuse me. If we now use Fock states, you can see the oscillations that I've been showing you before, and we clearly beat the classical limit and are in the non-classical regime with this. If we do that with the Fock state n equals 2, we also beat the classical limit, but we see no further enhancement because the higher slope, the steeper slope is all eaten up by a reduction in contrast. And I should mention that this work was in a very fruitful collaboration with our theory colleagues within our collaborative research center here. Now, to actually prove that we don't only have an enhancement in Fisher information, but that we actually can use it to enhance a measurement, we've made a displacement or amplitude or force measurements. Here you can see what we call an Allen deviation. That's sort of the integrated statistical uncertainty as a function of the number of experimental cycles. The red line designates the border to the non-classical region, and using the vacuum state, we're slightly above that due to experimental imperfections. Now, if we use the Fock state n equals 1, we're below that theory line here by 1.3 dB, and we're below the experimental values using the vacuum state by 3.6 dB, and that means effectively a reduction in averaging time by a factor of 2, which I would consider non-negligible. Now, if you care to turn this type of displacement measurement or amplitude measurement into a force measurement, you can do that, and you would arrive at 100 yoctonewton per square root hertz. And that's, yocto is 10 to the minus 24, actually. Now, to show that we can use the same resources, namely the Fock states, not only for displacement measurements, but also for frequency measurements, we've made a Ramsey-type frequency measurement, trap frequency measurement, so measurement of the oscillation period of the ions in the trap using the vacuum state in blue, the Fock state n equals 1 in red, and Fock state n equals 2 in green. And you can see that the line width of these resonances becomes smaller and smaller due to the quantum interference effect. And we've also turned that into a frequency measurement that you see here in a similar plot with the Allen deviation here. In contrast to the previous plot, you see here that at one point the data starts drifting off, and that's because our trap frequency is not sufficiently stable. It starts drifting away, and the onset of the drift you can see here. If we do that with the Fock state, we're clearly, again, below the red line in the non-classical regime. And in this case, it's actually, it would allow us to determine the trap frequency to much higher accuracy before it starts drifting. And so if we set that up in a feedback loop, we would have a much higher bandwidth in our feedback loop to stabilize, for example, the trap frequency. And I should mention that there's complementary work also using Fock state metrology that will be presented by D. Leibfried this afternoon. Now, to sum up, I hope I could convince you that we've made the first steps towards controlling molecular ions by demonstrating simple quantum logic type spectroscopy on the molecule. And we plan to enhance that in the future by combining that with Fock state metrology to improve our state detection capabilities. Now, what do we want to do once we have that toolbox? We want to aim at measuring a possible variation of the electron-to-proton mass ratio in oxygen plus. That molecule has a number of advantages, one of which is that the estimated systematic shifts in that molecule for that type of overtone spectroscopy from nu equals 0 to nu equals 4 is at the level of 10 to the minus 17 and would allow us to improve by 3 orders of magnitude over previous result obtained with SF6. Now, what do we need to actually implement this goal? We need a source of oxygen. We have set up a molecular beamline with differential pumping to be able to ionize O2 molecules into our Paul trap actually state selectively. And then we want to achieve deterministic row vibrational state preparation, and you will also see in Didi's talk how the NIST group achieved such a scheme. And then ultimately, again, our goal is to control and perform spectroscopy on molecules on par with atomic ions. Now, since effectively all problems with molecules are solved with the quantum logic spectroscopy toolbox, we've been looking out for new frontiers, and the new frontiers is spectroscopy of highly charged ions. Now, for highly charged ions, all your wisdom on energy scales are gone, and because everything is scaled to much higher energies, and you can, in this case, have optical transitions between fine structure or even hyperfine structure levels, and you can take advantage of level crossings. And why do you care even? Because these highly charged ions are actually exquisite candidates for qubits, for optical clocks, and some of them are the most sensitive species for probing, for example, non-standard physics. And so for this reason, we've set up an experiment in Braunschweig where we generate highly charged ion in this electron beam ion trap in a collaboration with José Crespo from Heidelberg. You can see here this device. We eject the highly charged ions in this beamline, bend them around, do a charge to mass selection, slow them down, and then inject them into this cryogenic Paul trap operated at 4 Kelvin, where we have trapped single beryllium ions or clouds of beryllium ions, and then we hope to achieve within the next few days actually a situation like this, where we have, for example, argon-13 plus trapped and sympathetically cooled in a cloud of beryllium ions, and then commence with quantum logic spectroscopy. If you want to know more about this, visit me at my poster this afternoon. And with this, I would like to thank my group for all the excellent work, in particular Fabian Wolf, who was the lead PhD student for most of what I've presented today. And with that, I thank you for your attention.